So we've been talking about internal energy in microscopic systems, and we talked about emission of photons by atoms that were somehow had gained energy, were in some excited state, were decaying down to a ground state. And just to make it a little bit concrete, I'd like to take a minute and just look at some of these, look at a couple examples. You're not going to be able to see very well because even after I turn out the lights, these lights on the side provide lots of light pollution, unfortunately, but you're going to be able to do this in detail in lab next week. So what these things are that you have, these diffraction gratings, they work like a prism. They spread out, they bend the path of photons of different energies, different amounts, so that if you look up at the lights, as most of you have been doing, these nice white lights produce a nice rainbow spectrum. These are interesting lights because they're sort of deceptive. They're not really, things don't look the same as they would with an incandescent light bulb. In fact, you see these discrete stripes of purple, blue, sort of cyan, orange, yellow, red, right, when you look at the lights. So actually, I think these tubes are coated with compounds that are called phosphors, and when they get hit by energetic photons from the gas inside, then they emit light at these different energies, and so it looks white to you, but it's not entirely continuous. So remember we talked about hydrogen atoms with our very familiar electric potential energy curve, and we said that according what Niels Bohr found was there were only certain values of K plus U that the system of electron plus proton could have, and these values were calculable by the energy of the nth, where this starts out as n equals 1, 2, etc. state, was minus 13.6 eV divided by n squared, and we calculated some of these things. And so if you ran electrons through a gas of hydrogen atoms, and it really has to be a gas of hydrogen atoms, not diatomic hydrogen molecules, which you can do if you just have a very low density gas. They will dissociate. We should be able, some of these, the differences, if one of these atoms is in some excited state and it emits a photon of an appropriate energy and makes a transition to a lower energy state, some of the photons are not detectable by our eyes. They're often the UV and X-ray, but some are. And so you should actually be able to see them, but since it's not going to be a continuous spectrum, what you see when you look at one of these tubes, this one's hydrogen. You see when you look at this tube is going to be a bunch of different lines. Now the way you have to do it is you have to hold the diffraction grating very close to your eye and then look a little bit sideways. So let's just try this and see what we get here. Yeah, if you didn't get a diffraction grating, please do come up and get one. Okay, so let me move this as far over as I can so you're not looking directly at the light on the side. This is hydrogen, atomic hydrogen in this tube. And we're running a beam of electrons through it. And even without the diffraction grating, you can see that this does not look like white light. Okay, you can see that so it looks, even without the diffraction grating, looks pretty red. Now, you see the image of the tube, but then if you look off to the side, you should see some lines that are not the same color as that tube, right? Do you see, for example, a sort of cyan-colored one? Yeah, maybe some purple ones. If your eyes are, well, Yeah, there's kind of an orange one off to the side. So those do correspond, the energies of those photons do correspond to energy differences between these levels that we calculated using Bohr's model for a hydrogen atom. Now, somebody asked last time, are these energies different for different atoms? And the answer is absolutely yes. And so let's try helium, which is only a slightly more complicated atom than hydrogen. You got 2 electrons. But hopefully what you can see here is that the colors of the lines you see here, and this is what we're talking about, emission lines. These are spectral lines. They're images of the bulb, but with photon energy spread out. So here you can see, I think pretty clearly, what are you seeing? A purple one, sort of greenish one, yellow, red, yeah. And in fact, there's probably pairs of lines in there somewhere. So we're seeing a very different set of photon energies than we saw for hydrogen. Let's try one more, which is kind of nice. So this is Mercury, which is the atom that was actually yes, it's a gas of mercury atoms, even though mercury is a liquid at room temperature, but okay, so that really looks different, right? A lot bluer. So almost no photons down in the red range, right? You're seeing, yeah, very little red. So what we're seeing is the effect of mercury atoms in an excited state losing exactly the right amount of energy to go from one energy level to a lower energy level, emitting photons, some of which our eyes are good detectors for. So we actually can see this emission spectrum. And in lab next week, you'll be able to look at this in a much darker and nicer environment, because it's actually it's very annoying to have these lights on the side here, but you can darken the lab rooms pretty well, and so you'll also be able to get a lot closer to the sources, so you can actually see it. But that's the basic idea, and it's very real, right? I mean, you see these different colored lines instead of just a continuous rainbow. And so what we're seeing is transitions corresponding to, we're seeing photons emitted at energies corresponding to differences between energy levels. And of course, since you can have different pairs of energy levels, you get different photon energies. So that's the basic idea of what we're doing here. Just to remind ourselves about the kind of calculations we've been doing, let's think about this here. So this is a hydrogen atom. It's initially in the ground state. So there's actually a lot of terminology flying around here. So some of the things we need to know. So what does ground state mean? The lowest possible energy level for that system. So for hydrogen, this is the ground state. So negative 13.6 eV. For other atoms, it's different. So the question is, this atom absorbs a photon, which actually results in ionization. What does ionization mean? It means you're making ions, right? And in this case, what it means is you pull the electron and the proton apart. So you've got a proton and an electron. And so what was the energy of the photon that was absorbed? Now, it's true that we haven't really discussed this, but those of you who said 13.6 eV, which is indeed the correct answer, may have been thinking about something to do with what we've talked about bound systems and spacecraft escaping from the Earth or a comet escaping out of sun's orbit. Remember that if K plus U is negative, then the system is bound. But if the sum of kinetic and, in this case, electric potential energy gets to be 0, that means that enough energy has been put into the system that these two objects could be extremely far away from each other with 0 kinetic energy. So if the system starts out here in the ground state, then we want to get up to K plus U equals 0. It looks like, in fact, we need a photon with enough energy to go from negative 13.6 EV up to 0 EV to separate these two things. So this energy difference is indeed 13.6 EV. Now, 2 was a popular answer, negative 13.6 EV. Why is that not a correct answer? A photon can't have negative energy, can it? Why not? Because it's all kinetic energy. So the energy of a photon is always positives. So in the process we're talking about here is hydrogen goes to proton plus electron. That's the final state. That's the initial state. So we have hydrogen plus photon, really. Photon plus, make everything the system. So photon plus hydrogen goes to, and so we have, we'll just use the energy principle. E final equals E initial. We take everything as the system. And so we have the kinetic energy of the proton and the kinetic energy of the electron and the rest energy of the proton and the rest energy of the electron is equal to, well, we have the rest energy of the hydrogen atom plus the energy of the photon, which is, oh, and we forgot the electric potential energy. That's important. So we better have that. This is final. That's initial. Now some of these things are 0 and some don't change very much. So we haven't really transmuted hydrogen into some other element. We haven't been doing fission or anything. So we're not really worried about rest energy changes here. But what we are worried about is there's electric potential energy and there's kinetic energy. So whatever we had, plus, so we have K of the, I'm going to put K of the hydrogen atom. It's really K plus U for the electron proton system. We'll write it out. K proton initial plus K electron initial. So we'll be very clear. Now some of these things are 0. So in the final state, just barely getting separated, 0 kinetic energy. If these things are far enough away from each other, what's the final electric potential energy? 0. And so that means that what we've got here is K plus U for the hydrogen atom, which we know was a negative 13.6 eV, plus the energy of the photon, is equal to 0. So the energy of the photon had to be plus 13.6 eV. Now you kind of did this in your heads, but if you actually write it out, which is okay in this case, if you actually write it out, you're not going to make sign errors. But you're not going to make sign errors if you think about what the meaning of this energy thing is, too. So, okay. So now I want to actually look at an example of the kind of problem that Niels Bohr actually had to do to figure out what the values of the energy levels for this bound system hydrogen atom really were. And what Bohr started with was just the energies of photons emitted by hydrogen gas, which he could measure using a diffraction grating and a standard. And so what we're going to do is consider some imaginary atom that's not hydrogen. And we're going to try to deduce what the energy levels of this electrons plus protons system are just by looking at the energies of the photons that are emitted by when you run a beam of electrons through the gas and excite it. So that's what's happening in these tubes. There's a beam of electrons that runs through the gas, crashing into these things, and excites it. So here are the energies of the photons that are emitted by our system. Um, 3 EV, 4 EV, 7 EV, 9, 13, and 16 EV. Now remember that visible photon energies are from about 1.8 EV to 3 EV, something like that. So, in fact, this is probably not your eye you're using to detect these things. Your eye might see these, but we're up in the ultraviolet or whatever range before. And we also know something else about this system. We have reason to suspect that there are 4 energy levels. So therefore, let's see if we can construct an energy level diagram, which means we're just going to draw horizontal lines for the values of K plus U for this bound system that we know exist. So take a minute and just think about how you would do this. Okay, talk to your neighbor, think about how you'd start figuring out. Okay, so this is not a right equation plug in numbers problem. This is it's a trial and error problem, but you can approach it by making some intelligent beginnings here. So one of the things to notice here is that we know the energies of the highest energy photon that's emitted and the lowest energy photon that's emitted, right? So what is the highest energy photon that's emitted going to correspond to here? The biggest difference, the top to the ground state, isn't it? So we can start out by saying, well, we'll draw if this is the ground state, and that's going to be the top state, that biggest energy photon corresponds to that difference. So we can draw an arrow here and say that this is going to be 16 eV, the difference between these two states. Now, does that tell us the absolute value of this energy? It doesn't, does it? It's going to be negative, but unless we actually knew the ionization energy, we couldn't figure this one out. Okay, now we have, what are we going to do with the smallest energy photon? So you want it to be the one below the top, okay? So you're saying that this energy difference would be 3 eV. Is that what you're saying? Okay. Now let's check. We already have a situation where we can check something to see if this is right. How do we check? What about this energy difference? That better correspond to one of the photons we detect, hadn't it? So this is going to be what? 13 eV, looks like here. And that's good. So we've taken care of this one, and that one, and that one. Now, what are we going to do? Now we have to try a few things. But look, notice how far we got with just those two photon energies. Okay, so one suggestion is the third one from the top would be the second smallest difference. So what do you want to make that? 4 eV from the top. It could be. From the second one. Oh, you want it to be from there. Okay. So we want it to be this would be 4 eV. Okay, what about these other photons? Where's our 7 eV photon coming from? Okay, that's 7 eV. What about 9? These two. And the last thing to check is, are there any other possible photon energies that could be emitted? Have we actually accidentally got any extra? We've got all the possible transitions from the top, and so it looks good. Now, so that was very good. What about this energy level diagram, though? Suppose I said that this one was 3 eV, and that one was 4 eV, and that makes this one 9 eV. This is still 16 eV. Where's the set? Here's 7. And there's our 13, right? So that would work too, wouldn't it? So we actually have two possible answers, and it looks like we can't actually tell which is right. And that's true. We can't from emission experiments, but there is an experiment we can do to determine which of these diagrams is right. And it's the other thing, it's an absorption experiment. We shoot a beam of photons with all these different energies at a sample of this atomic gas. And we look on the other side to see what photons are missing, what photons got absorbed by the sample. There are fewer of those. Why does that tell us? Why would that tell us which is which? Because there's an effect of temperature on the population of these different energy levels. If we go back to hydrogen, so here's our hydrogen potential energy. Notice that we also were not able to draw a potential energy curve here, but going back to hydrogen, this minus 13.6 electron volts, etc. It turns out that at low temperatures, almost every atom in your system is in its ground state because there just isn't enough energy floating around to keep raising these electrons to these higher energy levels. Remember that we needed to do something sort of extreme, like collide high energy electrons with Mercury in order to get it up there. So at low temperatures, we can say that almost all of the atoms, the objects in our system, I'm going to say objects because this is actually true for what we're going to talk about. They're in the ground state. So what we're going to do is an absorption experiment. Here's our sample. We're going to take a beam of light that has all those different photon energies, shine it at our sample, and put a detector over here to see which photons get through and which ones don't. And if photons have been absorbed, then it's got to correspond to a transition between the ground state and some other state. So let's figure out what we would get if we did an absorption experiment and the system really looked like this one. What energies of photons would be absorbed by this system? Now, see, we're starting, everything's in the ground state, so you said 7, so that would be, so this is absorption going up, so that would be 7 eV, wouldn't it? What else? 3 eV. And 16 eV. And that's it, isn't it? What about this one? I'm not seeing it. Oh, 9. Yes, 9. Sorry. 9 eV, so that's this one, isn't it? And 13 eV, this is from the ground state to this is the first excited state. That's the second excited state, and this is the third excited state. And what's the last photon energy we'd see? 16. So for absorption, I'll write it up here. This one would absorb 16, 13, and 9 eV, whereas this one would absorb 16, 7, and 3 eV. So an absorption experiment could tell us which of these schemes was correct. I'm waiting for someone to ask about why do we not see this 9 eV photon absorption here? All the things start out in the ground state, and once they get excited, even if it absorbs one of these 7 eV photons, it emits it very quickly and makes a transition back to the ground state. That's why you could see all the photons coming out of those tubes. So why doesn't that photon get to your detector? Because what happens is consider shooting a laser beam, a straight beam in of photons. Here's your photon beam coming in. Here's the beam coming out, going to your detector. When a photon gets absorbed, when the atom emits it, re-radiating, it has an equal probability of going in any direction. So very few of them actually get to your detector. So that's why you see these missing photons. Okay, good job. I should add one thing about ionization, which is the clicker question we just did. What if you add more than 13.6 eV? What happens here? That actually turns out not to be true. What happens is that's enough energy to break the bond and just give the proton and electron more kinetic energy. Why? Are there states up there? Yeah, there are energy states up here, but they're no longer separate, discrete states. Now it really is a continuous. It's called the continuum. And so once you get this thing unbound, then the unbound proton and electron can go back to having any positive value of K plus you want. There's an infinite number of states there. So it does actually work to use a higher energy photon.